Jack Jackson. In this video, we'll derive a formula, shortcut formula for the derivative of the tangent function. So the proof is pretty straightforward here. We do not have to go back to the definition of the derivative in this case because we have some pretty cool little rules and formulas and identities we can use. The first thing we're going to notice is the derivative tangent of x can be rewritten as the derivative of sine x over cosine x. So we use what's sometimes called a quotient identity there to rewrite tangent of x in terms of the sine and cosine functions. Now we have a quotient, so we can use the quotient rule. Quotient rule says it's the bottom times the derivative of the top minus the top times the derivative of the bottom or the bottom square. So that's cosine of x times the derivative of sine x minus sine x times the derivative of cosine x over the cosine of x squared. So the derivative of sine x is cosine x, and the derivative of, let's see if I can point to it here for you. The derivative of the sine x is replaced by cosine x. That's what we just proved it is. And derivative of cosine x is minus sine x. You see where we put these parentheses, so we know this is multiplication, not subtraction here. Now cosine x times cosine x is cosine square of x. And minus times minus makes a plus. Sine of x times sine x could be written as sine square of x, or sine of x quantity squared, which is what this notation means. Do you see anything else you can do? Well, hopefully you remember the basic Pythagorean identity that cosine square of x plus sine square of x is really just 1. Another way to write 1 over cosine square of x is 1 over cosine of x quantity squared, which is secant of x quantity squared, which we could write as secant square of x. So we just proved that the derivative of tangent of x is secant square of x. Now here are the graphs here. For the original function in blue is tangent of x, and its derivative is in red, which is secant square of x. Notice that secant square of x, of course being a square, is always going to be positive, or, well, not even 0, just strictly positive in this case, which means that everywhere the tangent is defined, the derivative is also defined there, which is secant square. So the tangent is continuous where it's defined, but it does have these discontinuities where we have the vertical asymptotes. And notice that the vertical asymptotes of the tangent are the same vertical asymptotes of its derivative, secant square of x. Notice everywhere the tangent is defined, it has a positive slope, so that on each individual piece, as long as we don't jump over an asymptote, then the original function is increasing, so its derivative will be positive. And that's all seen in this picture. Notice that the original function, tangent of x, has x-intercepts, which are actually also inflection points, and that occurs at integer multiples of pi. And at every one of those places, it's an inflection point going from concave down to concave up. So the second derivative is has a 0 at these places where the inflection points occur on the original function, and they're the same places where the derivative function has a minimum. Okay? So there we get that. The next video we'll go ahead and talk about cotangent, secant, and cosecant.